I've now been at EPFL for 4 years, so I'll tell you a little bit about our research. This is our campus. You can see we're by Lake Geneva. This is the Alps in the background. They're a little bit hidden, so it's a very nice place to work. There's a lot of interesting buildings on that picture. I work in none of the interesting buildings. I work in chemical engineering, which is the most boring building here, but it's still a pretty nice place to work. So I'm going to be telling you a little bit about our work on biomass conversion and catalysis. And if there's one theme that will sort of come back again and again, is that the difficulty in this type of chemistry is often not in getting the reaction you want to happen. Instead, the difficulty is preventing the reaction you don't want from happening faster than the one you do want. And so that's why I talk about unfavorable kinetics and how you have to fight them in my title. But before that, I'd like to give you some context, and it's a context in motivation, and it's a context where in today's world we're really surrounded by carbon, and especially fossil-based carbon. And so normally when I say fossil-based carbon, I think most people think of this, right? But it's not just fuel. It's also all kinds of products that we live around. It's textiles, it's plastics, detergents, and even some of the food we eat is made from crude oil. And so the point of this slide is a little bit gimmicky, but the idea is just to show how far the tentacles of crude oil really reach into our society. And we can't get rid of our dependence on crude oil by just switching to electric cars, for example, right? We need carbon somehow. And so, and specifically, we need renewable carbon. And if we sort of turn to where can we get renewable carbon from, well, there's really only two big sources of renewable carbon on the planet. There's atmospheric CO2, and there's plants. Those are the big sources. And just by the limitation in this list, and the difficulty it is from taking something that only has one carbon and building something complex that has 6 carbons, it's virtually guaranteed that plants will have an important role in supplying some form of renewable carbon. Now, I can't stand here and say it's going to produce all the fuel in the world, probably not. But it's virtually guaranteed that it will be an important player in the products and chemical market in the future. So all of you probably know this, but just when I talk about plants, the largest source of terrestrial plant is Lignocellulosic Biomass. This crowd probably doesn't need this introduction, but I'll be very quick so we're all on the same basis. Lignocellulosic Biomass is all the non-edible plants that you see around you, trees, grasses, leaves, things like that. And lignocellulosic biomass is formed by plant cell, and most of the weight of a plant cell is found in its plant cell wall, well over 90%. And the plant cell wall is formed by macrofibril and microfibril mixtures of 3 biopolymers, which are basically cellulose, which is a polymer, linear polymer of glucose, hemicellulose, which is a heteropolymer, mostly xylose, but there's also some other stuff, so these are both polysaccharides. And finally, there's lignin, which is not a polysaccharide. It's made of these phenylpropanoid subunits. It looks complicated, but when you really zoom in, it's actually always a phenyl group with 3 carbons. Phenyl, 3 carbons, phenyl, 3 carbons. So I defend the notion that lignin really isn't that complicated, especially if you treat it right. And it's especially interesting because it's the largest natural source of aromatic molecules. And there's a lot of aromatic functionality in today's chemicals. So, and that's something that's especially difficult to build with a 1 carbon molecule like CO2. So I think that there's an especially interesting source for our chemical industry. And what my lab asks is basically, my lab is interested in answering the question, how can we transform these 3 biopolymers into petrochemical, either direct or indirect substitutes for petrochemicals. And the approach we follow is at least in its current form, is sort of a very targeted approach. And what I mean by that is we're trying to produce a limited set of molecules at high yield and selectivity. And we do that by trying to deconstruct the plant to a limited set of molecules, and then take these molecules that hopefully we've obtained at high yields and upgrade them using catalysis. That's our specialty, mostly heterogeneous catalysis, to these non-targeted petrochemical substances. And the motivation for this targeted approach is economical. So I tried to translate, I'll show you some prices, I tried to translate them in dollars. Basically you can produce, and this is probably debatable, but plant matter you can produce it somewhere between 7 to 17 cents per kilogram. I'm sorry I didn't translate it to pounds. I have a lot of trouble with the non-metric system, so that's the best I can do. If you compare that to crude oil costs about 60 cents per kilogram. And this is a mixture, but it doesn't have any oxygen. So if you were to remove oxygen from here, it's about half of the weight is oxygen. You would get to something that's, you know, anywhere from around 20 cents per kilo. And so there's really maybe 30 cents a kilo. So there's really not much room to build a process between those two prices. I mean, it's a very tight, you have to build a very tight operation. If you go to something like gasoline, which is a little more refined, price goes up a little bit. Jet fuel is even higher. But if you look at chemicals, that's where it gets really interesting. Because most sort of bulk chemicals are in the range of $1 to $12 a kilo. And that's where there's a real economic driver. So at least I think the first processes, the first successful plants that we'll build will be based on sort of producing individual chemicals because that's where the driver is, and hopefully de-risk the technology for these other components. So that's what we've been trying to kind of target. And in the lab, we work in three areas. We work on biomass deconstruction, where we're actually trying to produce these molecules from plant matter. Then we try to develop catalytic routes, where we take some of the molecules here and make direct or indirect substitutes. And finally, we work on catalyst synthesis, where we basically are trying to build catalysts that can deal with the really kind of nasty junk that we produce here that's nothing like petroleum and much more difficult to deal with. So I'll go a little bit at length. I'll give you a longer story on our work in biomass deconstruction, and then I'll tell you two brief stories on catalytic route development and catalyst synthesis that kind of go with the deconstruction story. So let's start with deconstruction. In deconstruction, the goal is basically to depolymerize these three biopolymers. So we want to produce glucose from cellulose, xylulose from hemicellulose, and some sort of phenylpropane monomer from lignin. Okay, that would be the goal. And so one thing that I think is kind of nice is if we think, okay, if we want to do that, what bonds do we need to break? So if I highlight them here, you'll quickly see there's one bond that appears more than the other. It's this ether bond. It's carbon, oxygen, carbon. So we mainly need to break ether bonds. There's a few carbon-carbon linkages within the lignin. In a typical lignin, it's 20 to 30% for a hardwood, a little more for a softwood. And this is always something interesting. If you think about, well, how challenging is it to break ether bonds? Well, it's not necessarily, at least from an engineering perspective, it's not that challenging because it happens quite readily, even in just water in weakly acidic conditions. Somewhere between 80 and 200 degrees, if you put an ether bond in water, it'll start breaking, right? It'll hydrolyze. So you could ask the question, why is it a challenge? And why is, among others, Michigan State getting almost $1 billion to try to tackle this challenge, which is basically what GLBRC, they were doing other stuff too, but this was one of the challenges, right? Well, I would argue that the challenge is not so much to get this reaction to happen. The challenge is avoiding that at the conditions at which this happens, basically, these guys undergo degradation. So I'll give you an example. If from cellulose we want to produce glucose, from hemicellulose we want to produce xylulose. And the issue is, and this is especially an issue for cellulose, is under cheap conditions like pure water, water with a little bit of acid, these reactions will get out-competed by dehydration reactions where you produce these furanic molecules. And once you have these furanic molecules, so I'm trying to make the arrows roughly proportional to my rates here, those can very easily condense to these things we call humans that have a lot of carbon-carbon linkages. In lignin, it's a very similar but not completely identical story. So if you start with lignin, ideally you want to just cleave this bond and you could make monomers, right? Here, this is the BAO4 bond, the most prominent linkage of lignin. And if I was able to do this with 100% selectivity, I'd get a yield of about 50%. Now, the reason it's 50 and not 100% is because of these carbon-carbon linkages in the original lignin. That those, with current chemistries, we don't really know how to break them selectively. So this is just based on breaking the ethers. Now, the problem is that this reaction almost never happens because there's a far, far more favorable reaction that happens where you have the dehydration of this alpha hydroxy group. You form this intermediate that looks a lot like styrene. And just like styrene, boom, it repolymerises and forms this condensed lignin. And this is the form that almost all the lignin that you see around you has, right? This is the form that all the lignin that comes out of pulp and paper plants has. This is the lignin that comes out of most pretreatment processes. And if you try to upgrade this, you never get 50%. You get maybe 2 to 15%. 15% is extremely generous. That's if you extract the lignin really gently. If you get lignin from Sigma and try to upgrade it, you'd be lucky to get 2%. If you get Kraft lignin, you'd be lucky to get 1%. So hopefully here you see a theme that's appeared. And the theme is that you start out with something that it's fairly ordered, and it has bonds that are easy to break, these ether bonds. And you end up with something that's randomly repolymerized and has CC linkages, which are almost impossible to break. And so you're sort of losing value along this process. So what solutions exist? Well, for polysaccharides, the oldest solution is to put polysaccharides in a very high sort of ionic environment. So one of those would be, the oldest one is concentrated acid, more recently it's ionic liquids. And what happens there is basically the ions will intercalate, break the hydrogen bonding, and we'll be able to solubilize the sugar, to solubilize the lignins. And once you have soluble sugars, then this reaction, this depolymerization reaction, can be fast enough that it outcompetes these reactions. Okay, that's essentially what's happening. Again, look at my arrows, I'm trying to represent this a little bit. The other, even more popular solution is to use enzymes. So there the trick is you have to start with polysaccharides that have a high surface area, and then you're doing the exact same acid-catalyzed hydrolysis reaction, but because it's occurring in an enzyme pocket, you get 100% selectivity, so you don't have to worry about these reactions. Okay? Now, for lignin, there's no real industrially even relevant solution, but there's a very old solution that's been around since the 1940s, where basically what you do is you take wood, you mix it with a heterogeneous metal catalyst, and basically you run it under hydrogenation conditions in a solvent with some hydrogen pressure. And under those conditions, you can more quickly hydrogenate either the intermediates or the lignin directly to this stabilized form that no longer condenses, and eventually you can even push it to produce monomers at 45 to 50%, so roughly theoretical yield. So this process has been known since Hibbert's group published it in the 1940s, and more recently, because of the interest in lignin, there's been an explosion of quite nice work actually by a lot of big catalysis groups around the globe that more and more are sort of finding ways to make it more selective, use cheaper catalysts. They're trying to recycle the catalyst. Now the issue is still that if you start with ruthenium and carbon and wood, you end up with ruthenium and carbon and cellulose after this process. And good luck separating those two in sort of economical process. So the way I would characterize these is basically all these solutions, what they're doing is they're all expensive to various degrees. And what they're trying to do is they're struggling to create what I would call a kinetically favorable environment. And so the way my group approached this is say, okay, let's stay in what's not a favorable kinetic environment, but just try to prevent carbon-carbon bond formation. And specifically what we were trying to do is we were trying to say, can we find a reversible reaction that's more favorable than these condensation reactions? And we started thinking about this problem for lignin. And so I'm a chemical engineer, so I only had 2 years of organic chemistry classes, so I had to go with a very simple reaction. Unfortunately, we noticed that on lignin there's this diol functionality, and a very well-known chemical reaction is you can get a diol to react very favorably with an aldehyde. And when it reacts with an aldehyde, it forms this 1,3-dioxane structure. If it's a very aggressive aldehyde, it'll sometimes hydroxymethylate the ring, and hopefully you can get this to happen without more favorably than condensation. And in the first part of the talk, I'll tell you how we do this and how we upgrade this sort of protected or stabilized lignin to monomers. And then I'll tell you about how we can kind of do the same thing for sugars, because then they too have these double hydroxy group functionalities that we can get to react with an aldehyde. So I apologize for those who have seen the slide before. I'm going to show you one of the earliest experiments we did with the simplest aldehyde, which was formaldehyde. And here what we're doing is I'm using very simple organosolve conditions. So I'm trying to extract the lignin with an organic solvent, 80 degrees, some acid. And in one case, I'm adding formaldehyde, and in the other, I'm not. And this is what we saw, the exact same reaction. And what's really nice about biomass, you know, they say chemistry is kind of like cooking. Well, biomass chemistry is really like cooking. And this is a sign that you burned the soup, right? It's bad, basically. And so clearly something's going on. This is after we precipitate the lignin. You see very different color when we extract it in the presence of formaldehyde. This is after it's settled, very different density. And we can see the changes by HSQ-CNMR. So if we image the lignin that's been extracted without any aldehyde, and we try to image the zone of the most prominent bond, BO4, basically it's empty, meaning we've completely destroyed the signature of the lignin. Now the exact same conditions, but with an aldehyde, we see the signature appear of this 1,3-dioxane ring, but more importantly, we still see the alpha, beta, and gamma carbon, meaning we've preserved the lignin's backbone, basically. So it looked good from the extraction point of view, but what about upgrading? So here, we took this was beechwood at the time, and as a control, we did this classic reaction where you mix the beechwood, just to sort of see what the maximum yield could be. We mixed our beechwood with refined carbon and treated it at 250 degrees for 15 hours in methanol with hydrogen, really to get everything. And you see that just as others had shown before us, we get this roughly 50% yield of monomers, where we get 3 YSL products, or Stearingill products, sorry, and 2 YSL products. If we try to extract the lignin without any protection group, without anything, and try to upgrade it, we get way worse yields, less than 10%. This is the black lignin I showed you in the previous slide. Now if we run this exact same condition, but extract it in the presence of formaldehyde, you see that here we get almost the same yield as before, but if we optimize a little, you see that we basically get indistinguishable yields. The only difference is instead of getting our 5 original products here, we get the same 5 products, but also their methylated equivalents, because formaldehyde has added itself to the ring. Okay, so, and what's important here is that what this process now allows you to do is early on is to fractionate your plant very cleanly into 3 fractions without sacrificing the upgradability of any of the fractions. So this is an example from birchwood, where we take 5 grams, that's 4.5 once you remove the extractives, and you see we get 2 grams of cellulose, 1 gram of this functionalized xylose, I'll come back to it, which is liquid, and 1 gram of lignin, which you can't see here, but it's actually purple, which is very interesting. And these are the actual, this is to scale, so this is all 1 gram, 2 grams. You see very big differences in density. And because you fractionated the plant, you can send each of these fractions on its own upgrading path and get very high yields from every single one of the fractions. You get near quantitative yields of the sugars to stuff, and then you get almost this 50%, which is near theoretical monomer yield from lignin. Now remember, the reason we're getting 50%, not 100%, is because of the original carbon-carbon linkages in the lignin that are just there, that appear during biosynthesis. And so if you want to increase this, one thing you can do is you can collaborate with people who do genetic engineering of lignin. So we did this. I had a long relationship with John Ralph at University of Wisconsin, where he did a lot of characterization for Clint Chappell and Rick Malin that had been developing this transgenic poplar that was very high in syringyl content, and because of that, and because of reasons that have to do with lignin biosynthesis, had reduced carbon-carbon linkages. And because it had reduced carbon-carbon linkages, well, you can get higher yields from it. And we can get close to 80%. Same thing, we can still get very high yields. Very high yields of the sugar. Now, what's interesting is you'll notice, so my arrows here are proportional to the amount that we're producing. You'll notice that my arrow hasn't gotten any bigger. Basically, when they engineer the lignin, it seems like the plant makes less lignin. So you're not actually producing more per weight of plant, but you're producing more, you're converting more, you're being more efficient with your lignin conversion. So that's something we don't quite understand, but there seems to be some response to the plant being engineered, and it produces less lignin. So what I've shown you up to now is basically we can extract lignin with formaldehyde. Sometimes you get this hydroxymethylation, and then when you depolymerize it using hydrogenation over ruthenium, well, basically you get this mixture of products. You get very high yields, but you get a lot of products, in part because of this methylation that doubles the amount of products, but also because ruthenium does some CC cleavage and only partially hydrogenates this terminal alcohol here. And so we wanted to work on making things more selective, and a very simple way is to use a longer aldehyde. Here I'm showing you propanaldehyde, because at least then you'll avoid addition to the ring. And that works very well. And by switching catalysts from ruthenium to palladium, we can actually avoid CC cleavage and avoid hydrogenating these terminal alcohols. And we can keep the same yield, but push our product selectivity over 90% with just these two products. And here, this is a syringal unit, this is a guaiacol unit, and this reflects the original structure that was in the plant. So you can't get better than two products if you're using a wild-type hardwood, because those structures are already in the plant. So we're pretty much pushing the selectivity as far as it can go in terms of that particular species. We were also interested in showing that we could do the same thing with oxidation. And here we kind of used the modified Shannon-Stahl approach, this two-step oxidation. It's easy for me to show the result. It was a lot of blood, sweat, and tears by my postdoc to try to figure out a method where he could, in one step, deprotect and oxidize. It turns out you have to do them both in one step, otherwise the lignin would basically condense, but we found that it worked well with DDQ, this hydroquinone, where we could aerobically oxidize it with nitric acid. And basically, then we do exactly what Shannon does, where we basically depolymerize it with a formic acid solution. The difference is, though, is that we're able to produce over 90% of just two products. And the highest in the literature, if you look around in terms of selectivity and lignin oxidation, is way lower. It's something like 30%. And what we really attribute this high selectivity to the fact that we're protecting the lignin structure until the very last minute. Okay, and that, we think that basically if you don't do that, the structure gets modified beforehand, and that's why you get the mixture of all the other products. And these are the products that the mechanism predicts, so it makes sense. You see the yields are a tiny bit lower, and that's because some degradation does happen. We don't systematically oxidize every single linkage, which is difficult to do on an oligomer, but it's not that far off from the maximum, which in this case, we used a different wood, so I think the maximum was a little lower than here. It was normally, we should have been able to reach 42%, we only reached 36%. But still, we're pretty close. And so, I've been talking a lot, at least for hydrogenolysis, that we can reach pretty much what I call theoretical yield. Okay, so what that got us, that sort of put in our heads that can we really correlate the structure of the lignin with the yields that you can get? And so the idea here, what we wanted to do was we wanted to extract the lignin, not just with our protection chemistry, but just extract it with different forms, in different ways, better or worse. Do our typical hydrogenolysis, detection of products, get yields, and see if we could somehow correlate that to the structure that we determined by NMR. The idea being that we could just take an NMR and know what the yields would be without having to do this destructive process. Now, the difficulty in this is to do that, we need to be able to do quantitative NMR, to know how many moles of a given bond is present. And with HSQC, this 2D NMR, that's difficult to do because the peaks of each different groups it depends on a lot of things, but in particular, it depends on the relaxation time during the NMR process of each of the chemical functionality. And to make a long story short, this changes for a given functional group on a given molecule, and that problem gets even worse when you have an oligomer, meaning the relaxation on the ends is much faster than the relaxation in the middle, etc. And there is a method to sort of counter that effect, and it's called HSQC0, and I'll try to explain it really quickly. Where basically what you do is you run 3 HSQCs, each at a different relaxation time. And then what you do is you measure the volume for a given functionality, and you extrapolate to a fictional 0 relaxation time, what the volume would be at 0 relaxation time. And that gets rid of this difference in relaxations between chemical functionalities and allows you to be quantitative versus, say, an internal standard. Okay? So that's the most advanced NMR talk I have in this talk, so don't worry. But basically, we were able to use this, measure quantitatively the different bonds, and just use a very simple model where we said one bond, one ether bond gives us one monomer. And this is our predicted yield versus our experimental yield. And essentially, we're able to predict everything within. So there's no parameter fit here. We're really saying one bond equals one product, and we're able to predict everything within a couple percent. And what this tells me is really that things in lignin are very much preordained by structure, right? The quality of what happens during depolymerization is entirely determined by how good your structure is to start with. And so you have to sort of be nice with lignin for it to depolymerize properly. And so that's all I wanted to say on lignin, so I'll just briefly summarize. And I just wanted to summarize by sort of giving a positive message that it's extraordinary how much the lignin field has changed in the last 5 to 10 years. Because I remember 5 to 10 years ago, people were like, ugh, lignin, it's heterogeneous, it's a mess, it's completely intractable thing to work with. And I would argue that that has really changed, right? Because we can upgrade it now at pretty much theoretical yields, we can get high selectivity, and we can predict what's going to happen entirely based on structure. So I'm not taking fully credit for the entire advancement of the field. I'm just saying it's a really exciting time, I think, because of the progression. And it's not as nasty a substrate than people think, and it's thanks to all these groups around the world that have really been pushing the field forward. So that's sort of the story for lignin. So now let me tell you how we can use this chemistry for carbohydrates. So here, there's this similar problem where you'd like to produce xylose from hemicellulose, you'd like to produce glucose from cellulose, but you have this degradation problem that starts with dehydration of the hydroxy groups. And what I'll show you is we can use this same acetal chemistry to basically reversibly trap these sugars before they degrade. And we prevent their degradation because once you form the acetal, the first step towards degradation is dehydration. So if the hydroxy group is caught in this acetal, it can't dehydrate. But it's reversible, and this is quite nice, because these groups are favored under low water conditions. But if you put them in aqueous conditions, or more than 50% water, the sugars are favored. So you can kind of switch back and forth depending on the conditions you want. So let me illustrate this. So we started out, the easy one is for hemicellulose. So I should say it's not that hard to get very high xylose yields from hemicellulose, even using acid in water. Okay? But there's certain conditions where you favor this degradation pathway. So a typical example of that is if you're really trying, like in a pulp and paper process, if you're really trying to extract all the lignin, oftentimes the conditions are nasty enough that they'll destroy the hemicellulose. So this would be the case for sort of a harsh organosolv process. This is what I'm showing here. Basically, we're extracting most of the lignin, but most of the xylose is either going to degradation products in black or a furfural in gray. And this is the sugar we recover. Now, if we run these exact same conditions in the presence of, again, we're using the simplest aldehyde here, formaldehyde, you see I can push most of it towards this red bar, which is this product. And if I optimize conditions, I can push over 95% of the hemicellulose. So this is, again, I think from beech to this product. And this product is barely explored in the literature. And we're quite excited about it because we're kind of seeing it as a new intermediate. There's not that many intermediates that you can produce in one step from wood at quantitative yield. So it's something that we're kind of looking at exploiting. Now, the more difficult one is cellulose. So here what we did is we basically took the cellulose that was left over from the process I just showed you, where we were basically extracting lignin, so it's these cellulose-rich solids. And here, to have a little more control, we put it in one of these classic reactors that's well known in biomass, which is referred to as a flow-through reactor. So basically, the idea of these reactors is it's basically a tube that you pack your biomass in, and then you flow the liquid through the tube. So any solid stays trapped into the heated reactor, and the liquid sort of passes through and exits. And the idea of this reactor is you want to decouple the reaction that occurs on the solid with that occurs in the liquid. Because the solid is stuck in the reactor, so it'll see a residence time that's basically infinite, or as long as it reacts. Whereas the liquid's residence time is controlled by how quickly you pump it. Okay, so you can get 100% yield of glucose from cellulose using pure water in such a system. You just have to pump really fast. Now, if you do that, and this reactor is well known, you can do that, but you'll get really dilute glucose coming out of here. And so what's nice about this reactor, what's predictable about this reactor, is it creates a trade-off between yield and concentration. So this type of reactor setup was invented by the Germans in like the 1920s. So it's very well understood. And for a while, NREL, the National Renewable Energy Lab, was trying to optimize it for commercial production. So they mapped out this trade-off between yield and concentration. So here they show what yields you can obtain for what concentration. And in green, this is the zone that's accessible for cellulose. And to translate it, what it means is you can get high yields of glucose close to 70% if you're willing to accept low concentrations, around 1%. If you want high concentration or higher concentrations, around 3 to 5% weight percent, you have to tolerate really low yields, below 30% of glucose. So it's impossible to do both, and this is why this reactor never became commercial. So I can illustrate this with my own results, except here I'm using this GVL solvent, which helps things a little bit, but still not completely. And basically, on the x-axis here, I'm showing you a lower and lower solvent usage, meaning there's a longer and longer residence time for the liquids in here. So unsurprisingly, what's happening is the glucose yields are dropping, because basically the glucose has more time to degrade in the reactor. And so if I plot concentrations, well, you see initially as I start using less and less solvents, my concentrations go up. But eventually, my yields drop so much that I go through a maximum and my concentrations start dropping, even though I'm using less solvent. Now, let me show you exactly the same runs, but this time I'll add formaldehyde. So here, you see that I don't drop nearly as quickly, and under even some conditions, I can stabilize. And if I plot my concentration, well, I no longer go through a maximum. I just keep going up and up and up. And if I take this last data point, I'm basically getting a yield of 70% and a concentration of 5 weight percent. And by the way, this is after I've converted everything back from the stabilized sugars to glucose. So I'm really comparing apples to apples. And in the process, I can recover almost all my formaldehyde, at least within the error of my HPLC, or GC in this case. And so what does this mean? Well, if I go back to my little graph here and plot this data point, I'm way out here. So essentially, what the take-home message here is that with stabilization, you can really push back the traditional kinetic limitations of acid catalyzed polysaccharide depolymerization. And if you don't believe data, this is another one of my different colored pictures. This is just a batch reaction where we put some cellulose at 180 degrees and put it for the same residence time in the oil bath at 180 degrees for 3 minutes. And this is with and this is without formaldehyde. So again, you have this nice visual representation of avoiding degradation. The next question we have is we can produce these weird protected sugars quantitatively, essentially, from biomass, or very close to it. So the question we ask is, can these protected sugars basically lead to new paths to products, or at least lead to new reactivity? And so this is kind of falls under the umbrella of our new route, our catalytic route development. And so I'll show you one reaction where yes, we show that, I'll show you a very simple example where we show that yes, we can access new reactivity. And it's the very simple reaction of xylose to furfural that's been well explored, but that gives us a nice opportunity to show that we have new reactivity. So it's not that difficult to get high conversion of xylose to furfural. But here what I'm showing is a reaction at 160 degrees at which this reaction happens, but in a quite limited way. This is what you see here. So basically I'm showing xylose conversion, which is low, and a little bit of furfural production. And the mechanism for this is well known. Basically it's thought to go through ring opening, then you have an enolization or beta elimination step that leads you to then ring closing and furfural. Both of these steps have fairly high activation energy, which is why 160 degrees you basically don't see very much activity. Now, if you run the exact same reaction, but you add a Lewis acid, aluminum chloride, suddenly you bump up to a high, very high xylose conversion and high yield of furfural, even at these low temperatures. And the reason for this is because with aluminum chloride, you've unlocked a new mechanism. You've unlocked a mechanism where the aluminum chloride catalyzes a 1,2 hydride shift, where essentially this hydride moves up here, okay? And then you can go through ring closing to xylulose into this path. This has a lower activation energy in presence of a catalyst, and so the reaction happens faster. So this, everything I've shown you now, that's well explored in the literature. Now, what's interesting is what happens when we start not with xylose, but with our weird protected product. This is a complicated graph, but there's only one important thing in it. And it's the fact that both with and without the Lewis acid, where before we saw a big difference, here we see zero difference. We see high rates in both cases when we start with this. So if we thought, oh, this molecule is just deprotecting, going through ring opening and going through the classic mechanism, that's not possible because otherwise we would see a difference. And here we see no difference. And if we do, so one clue to what's happening is we did operando NMR, and the one intermediate we detected was this, furanose intermediate with this pendant hydroxymethyl group. And what we think is happening is that this is ring opening, just the same as xylose would. But the problem is when you ring open, you form this carbocation that would normally stabilize by forming the aldehyde. But here it can't because it has this group. And so essentially the only way for it to stabilize, I hope you can kind of see what's going on here, is through a rearrangement that's a hydride shift. So here, in this case, we were catalyzing a hydride shift. Here we're forcing a hydride shift because the starting product is essentially less stable. So we don't need a catalyst anymore. It happens on its own. So, and then we go through the same xylulose mechanism. So if you didn't follow any of that, it's not important. The only thing that's important is the fact that there's a blue here. And what blue means is that we've basically unlocked a new mechanism. And that's a lot of the activity now in my group is to say, hey, you know, there's only 5 or 6 molecules you can make from one step from biomass. Suddenly you've added a couple, which are these functionalized sugars. Can we unlock new paths with that? So that's, and we can certainly unlock new reactivities. What else can we do? And that's what we're working on right now. Okay, so how am I doing on time? With the questions. Okay, I need much less than that. So I'll just tell you some brief stories about catalyst synthesis that should be done in 5 to 10 minutes. So the goal here is to address what is thought to be sort of a transformational challenge for heterogeneous catalysis, because in the context of trying to switch from petroleum to renewables. So if you look at the molecular mixture of petroleum, this would be a typical molecular mixture. And what you see here, first of all, you see very little oxygen, right? Or no oxygen, meaning that this is actually a fairly unreactive mixture of molecules. They're all immiscible with water, so there's no water, and they're all volatile. So what that means is that the catalysis, the heterogeneous catalysis workhorse, has been able to sort of build itself in the chemical industry around gas phase, water-sensitive materials. That's what exists today. Now, if we try to switch to renewable substrates, first of all, they're all polymers, so they're not going to be volatile. There's a lot of oxygen, so they're super reactive. They usually come with a lot of water. They come with all their nasty stuff like proteins and salts. And so if we just use the classic catalyst, we'll get all kinds of problems. We'll have all these sort of oxygenated functional groups that will react each in their own way. We'll get low selectivity. We'll get leaching and sintering, meaning our catalyst will essentially dissolve in liquid phase when there's water around. And we'll get coking and poisoning, especially due to some of the proteins and salts and heteroatoms that are present in biomass. So basically, there's a challenge here. We need new materials to kind of bridge this gap. And the approach we've taken to the lab is what we're trying to do is we're trying to modify catalyst surface properties to somehow improve their activity, their selectivity, and especially their stability in these really nasty conditions. And specifically, the approach we've taken is to take classic, so here I'm showing a cartoon of a classic heterogeneous catalyst where you have the support, you have metal nanoparticles, and what we're trying to do is use liquid phase methods to deposit different forms of metal oxides onto the surface. The idea being that we can both protect the metal nanoparticles and maybe create interesting reactivity at the interface of the nanoparticle support and overcoat to try to improve activity and selectivity. And so we spent a long time developing the chemistry to really deposit these very thin, nanometer thick conformal overcoats on sort of classic high surface area catalysts. And here the challenge sort of joins the issues, the chemistry issues that I was talking about earlier with biomass. Because what you're trying to do, condensation is an easy reaction because you use precursors where things basically want to condense and form the oxide immediately. The trick is you want your condensation on the surface of the catalyst to happen faster than in the bulk because we want to coat the catalyst. So it's again fighting kinetics. And so there were various ways that we tried to address this. One was to try to develop a coating method using stoichiometric control. So these are always condensation reactions happening between a precursor and a hydroxy group. So one way we could do is basically project how much precursor was possible to add to a surface in a solution where there was no water around, so the only hydroxy groups available around the surface. So we would project what's the maximum amount of precursor that could be added to the surface, and we would basically inject that amount and let it react. So we would inject that stoichiometric amount, let it react. Once we were confident that everything had reacted, this is with an alkoxide, we would add water, the corresponding amount of water to what we just added, let the water react, reform these hydroxy groups, and that would sort of put down one molecular layer of our oxide, and we can just repeat the method and build up our overcoat. That's one method. The other method is to slow down the condensation kinetics, because the slower the condensation kinetics are, the more you favor heterogeneous nucleation on the surface versus homogeneous nucleation on the bulk. So one way to slow this guy down is to chelate it with a less reactive ligand. And so one of those would be these types of bidentate ligands, which make condensation a lot slower. So slow, in fact, that when you have this chelated ligand, you basically can inject it even in an aqueous solution, and you'll still favor heterogeneous nucleation on the surface. Another way is to cut water out of them. So both these processes use water, is to cut water out of the process entirely and use what's called a non-hydrolytic sol gel method. In this method, we mix the alkoxide precursor with an alkyl halide precursor. This forms something that's stable at room temperature, but it'll start condensing once you heat it up. And so what you can do is you can basically have it on your bench, but then inject it into a mixture that contains your catalyst at like 80 or 90 degrees, and it'll start condensing slowly on the surface. First, it'll liberate, here I'm showing the example with bromide, it'll start liberating the bromide acid in the first step, and then in the subsequent steps, it'll liberate alkyl halides. So basically, it's the oxygen from the original alkoxide here that's forming the oxygen in the final oxide overcoat. So here, I'm always showing these examples for alumina, but you can do it for any oxide. So we've done, oh, and by the way, these three methods, we get different types of overcoat, and it happens that this is the least dense overcoat that we form. You'll see it's very porous to a very high density overcoat that we form with. So we got this nice control depending on the method we use. Here are some, I'll show you some examples. We started doing this on model substrates. These are Nano Spheres. You see we can coat different types of oxide, different density. This is a very low density, very high density. We can coat high surface area stuff. This is mesoporous silica that has 300 square meters per gram. We can do nanowires. We can do these model substrates with nanoparticles. This is mesoporous silica with platinum, so metal doesn't interfere with anything. So we can coat all kinds of different catalysts. And so what applications are we using for this? So I'll just show you two very quick examples. This is a typical reaction you want to do from a biomass-derived product. So you can make furfural. I've shown that before. You can hydrogenate that to something like furfural alcohol. This is a nice precursor for certain types of resins, for example. And this works well over copper. Okay? Because copper will hydrogenate this group without touching the ring, essentially. And when you run this using a classic catalyst, this is my cartoon, this is our model catalyst, so it's pretty close to reality. This is what the reaction profile looks like. So we're running this in flow, and this is the catalyst activity. And what you see here is that it's deactivating. Okay, and it's going down, and this is on the log scale. So it's deactivating quite quickly. Most of that is due to furfural polymerizing on the surface. So you can burn it off, but you see that at each cycle, basically the activity is going down every time you burn it off. And the reason for that is because basically copper is leaching in solution and aggregating during the regeneration cycle. So now I'm going to run the exact same reaction, but instead I'm going to use the same catalyst where I've added a coating of aluminum on it. And this is the result you get. So basically here you see we still have this reversible deactivation where this is polymerizing on the surface, but every time we burn it off, it comes back to the original. So essentially, what our coating has done is it's locked down the copper and it prevents it from dissolving. So it's made it compatible with liquid phase water solvents because we were able to sort of lock down that copper and prevent it from aggregating. Another example of where we can use these effects is with a lignin-derived molecule. So this is a molecule, propyl-glycol, that you can produce at very high yields from, or at least high selectivities from softwood lignin because there's no syringyl groups. And let's say you want to make, it's maybe not the most interesting thing, but you want to make a jet fuel, so a C9 alkane. So you can do this in two ways. There's two main mechanisms. One is you hydrogenate the ring, and then you basically go through various hydrogenation pathways. Or there's a hydrogenolysis pathway where you directly cleave these bonds. Now this is the pathway that's largely favored on most heterogeneous catalysts, and that's a little bit problematic because oftentimes the reaction will block here and not go to the full alkane. So here I'm showing these results for platinum on silica, and you see exactly this. Here we're pushing up the conversion, but even as we're pushing up the conversion, we produce very little of the C9 alkane. We're staying blocked here. If I add some acidity, I can favor cleavage of these oxygenated groups by taking a support, like alumina, but only a little. Now, if I use our idea was maybe if we can create an acid site right next to the metal, we can get this to happen. So the idea was, if we put alumina on silica, silica alumina creates highly acidic groups, and maybe we can get the interface close to the metal and produce these close sites together and get a higher formation of the C9 alkene. So we tried this with our chelated overcoat, which is our medium density overcoat, and it doesn't really work. Now, if we run the exact same reaction with our non-hydrolytic overcoat, which is our densest overcoat, you see here, boom, we push everything, most of the product to the C9 alkane, and interestingly, the intermediates are now these guys as opposed to these guys. So it looks like we're pushing through the hydrogenolysis pathway instead. And we think what's happening is, because we have a really dense overcoat, we're maximizing the number of sites where we have metal and an acid right next to it. And when you have that bifunctional site, you can go through this hydrogenolysis pathway more favorably to get the C9 alkane. And this whole example is just to illustrate how I really think, and this is one direction, and this is my last slide, is that we want to sort of begin tailoring specific catalytic nanostructures to specific biomass-derived product streams. And I think that there's a big opportunity to bring this kind of material synthesis and reaction engineering of biomass together to produce specific products. So with that, I'll end there. I'll just acknowledge this is my group. Masood and Wu did a lot of the lignin work. My student Idna did all the stabilized sugar work, and Yuan Peng, Florent, and Benjamin do the catalyst synthesis work. As I said, I have some nice collaborations on sort of transgenic lignin with John Ralph, Rick Malin, and Clint Chappell. And I should mention the person who started this really nice stabilization work in my group was Lee Schweig, who's now an assistant professor at Virginia Tech. And these are various funding sources for biomass deconstruction. Mostly the Swiss government, so as well as for the catalytic route development. And our synthesis work is supported by the European Research Council. So with that, I'd be glad to take any questions.
Let's start with the students' questions.
Yeah, so now that was a big, I mean, basically when we say the word formaldehyde to people in industry, they're like, you know. So we've done a lot of work on that. So now we've mostly switched to propionaldehyde, and we found that, I was discussing this, I think, earlier, that we found that the aldehydes tend to condense amongst themselves and form very toxic dimers, which is a problem. It's very small, the reaction, but at large scale. So now we're using substituted aldehydes that prevent their self-condensation. Yeah, back there.
About the synthesis of catalyst,
Yeah.
you use the aluminum oxide and the silica.
Yeah.
These two stuff are used as the catalyst support or something.
Yeah, so what usually we use, in the case I show here, where we typically have a support, I mean, we could do either or, right? But we had a silica support, and we put aluminum on top. And that, what's interesting there is you create silica alumina sites at the interface, which have very high acidity. And because you did silica, you put a metal nanoparticle, and then you put the alumina, you're maximizing, the way I sort of picture it, is you're maximizing the amount of platinum nanoparticles, which have little acid sites at the interface. And that's what's creating the interesting catalytic activity. But in the case with copper, I just put alumina on alumina, because the only goal was to create sort of an effect where you lock down the copper. So we can basically, we can use this method for pretty much any oxide. Yeah. Sorry, I'm
The students.
giving the students.
For extraction of lignin, are you working with specific lignin sources or you always so many different sources of lignin?
We just use wood. The whole sort of, the message from my research, I think, is that if you use anybody else's lignin, it's bad, right? This is a way of protecting the original lignin in the wood. So I turn away a lot of, we were talking at lunch about how terrible I am at getting companies to work with me. Because they come to me and they're like, oh, can you use our craft lignin? And I'm like, I don't want to, I'm not interested in touching that. And so I'm like, but if you change your process, and then they just walk away. Basically.
And Jeremy, can you go back to the slide that we showed you using formaldehyde for making the clean out?
Yeah. Which one?
On the back, basically showing the formaldehyde reactions.
I think
in
it
the
was
reactions.
this one.
Yes. Sorry.
Yeah.
Okay. What you're showing here in these acidic conditions, and you're adding formaldehyde to lignin. Most of these structures that you're showing, like that's true that the formaldehyde is going to react with those locations, but you're also going to see that the methyl formations on the fossil unit.
Oh, yeah. Actually, one thing you're probably right. I drew this just to show that it was partially, I mean, we get all of these products.
Yeah, and then
So they're,
if that's forms and you're in acidic conditions, there's a high possibility that you're actually making Nova-like form.
I love that question. Yes, so everybody, when I started presenting this, everybody was like, you know, why this should never work because you'll just form resins. And I always tell people, yeah, that's true, but I wasn't a good enough chemist to think, oh, that might happen. That's why we were sort of dumb enough to try, quote unquote. No, so, but I think, so to answer your question, that doesn't happen. And I think the reason that doesn't happen is because when you're forming Novolac resins, you have to be at quite high concentration. And basically you need not only to form this group, but then you need two groups to come together.
Yes.
And so it's order 2 kinetics. And we're not dilute by any means. I mean, we're running this at 10 or even 20% biomass. But when you're running at 20% biomass, that's 20 times 20%, so lignin, right? So the lignin that's coming out, you're actually quite dilute in aromatic groups. When you make Novolac, the few times I've seen phenylformaldehyde resins being made, you're typically at, you know, a high concentration of phenol.
Yeah, or no, it's fine. But what's the temperatures that this reaction is not
80 to 100.
It's not exotonic at all.
Not that we can measure. No, I mean, so I think, yes, at these conditions, you can absolutely do this reaction, but the system is too dilute and it's order 2. I think that's the explanation.
But you're still talking about essentially raw wood that, so that presumably the amount of actually mobile small molecule fragments that could go, as you said, into biomolecular chemistry at any given moment is relatively small, right?
Yeah.
So that's another issue, and presumably you're sort of liberating bits from the surface of...
Yeah, that's another, there's steric hindrances, is what you're saying, or it's...
Well, I mean, to think of it in terms of biomolecular, like if you're talking about a solution of, soluble lignin or something plus formaldehyde, that's a fairly different...
So this is, so basically what's happening is, when we get our liquor is essentially, we've solubilized the lignin in the form of decamers, roughly, it's a distribution, but when we measure it by GPC, the average is about a decamer.
But you're solubilizing it in the process of doing the protection.
Yeah.
Yeah,
Right,
so
right.
at any given moment, there shouldn't be a whole lot that's ready to react with formaldehyde that hasn't already been protected.
No, but what she's saying is once you have multiple groups like this, they can condense together and form a Novolac type reaction where you would have another, basically, if you put another aromatic group here.
Yeah, as well, you've already started with bulking up, and presumably if you use propionaldehyde, it's even that much more.
Propionaldehyde, there's no, but we don't see it happen at all with formaldehyde, which a lot of, when I present this at conferences, I get that question a lot, like why isn't this happening? And I think it's probably a steric reason, and it's probably a concentration reason.
So then do you put the formaldehyde just directly into the GBL process, or how does...
So we typically, I think, no, it works with GBL. all these results were with dioxane, but it's the same thing. Yeah, essentially you make a solution where, I forget the exact proportions, but it doesn't work well if you have high amounts of water. Over 20% water, it doesn't work well because basically it'll shift the equilibrium away from the protection. So you need to be at below 20% water. And then, so we add 80% dioxane, 10% water, and 10% of a 15% formaldehyde solution or something, and some acid. That's roughly what I remember.
And then with the yield, something we were talking about earlier was when you talk about the monomer yields, that here you're talking about versus 47% of the original.
Everything
lignin,
is
right?
based on the original Classon lignin. So I never count the quote-unquote acid-soluble lignin because I always think that that's a weird measure. I don't trust that measure at all because it's this, absorption measurement, and yeah, I've in the literature a lot of people just report yields on Classon lignin, which is an imperfect measurement, but at least if you're consistent, I think it works fairly well.
And for the HSQC zero method that you were talking about, I think we have another method to confirm that the quantitative analysis is accurate, or do you have any internal standards in your system to confirm?
Yeah, so I mean, basically our method, so basically what we're doing here is, in one case, we're taking our extracted lignin, so we separate it in two, we send 1/2 to HSQC. So in the HSQC, we add an internal standard. And basically the result of this is to say, we have X millimole of beta-O4 bonds. And then we take the other half of our extracted lignin, do hydrogenolysis, where we also have an internal standard, we measure all these guys. And we say, here our prediction is to say, each beta-O4 bond equals 1 monomer, or each ether bond equals 1 monomer. And then we compare the yield we measure to the prediction based on 1 monomer equals 1 product, and this is what we get.
Is it, if you submit this work, is it ready that we can have access?
It's, and I have to poke my student a little. He has to do a few more control reactions, but basically it's ready to be submitted. Yeah, I'm happy to share.
That's going to be really nice to continue to deep work these processes.
Yeah, and I think it's, what I like about it is it really shows that the structure is controlling everything. And we've reached the limit of the conversion chemistry. At least, we've reached the limit of the brute force chemical conversion. I think you could still do nice things to make it happen at room temperature with electricity as opposed to hydrogen. But, yeah.
If there is no other questions, please join me to thank the meeting.